So this is the second sort of lecture where we're going through this regularities unseen randomness observed review paper and extending these notions of Shannon's information, but to try to answer the question, how do processes store information? Do they have memory? You know, a physicist would say, oh, the correlations between spins or atoms or particles in my system, we're using a slightly different vocabulary, that there's memory, because we have a much more mechanistic and computation theoretic view that we're heading towards, which is the subject of the spring course, being much more overtly computational. Not computation in the sense of we're doing simulations using computers, but I mean intrinsic computation in a process. Just like we talked about chaotic systems producing information being unpredictable, there's a much broader notion of information processing in systems that we're going to get to. And we'll make more direct connections to the theory of computation in the spring. Right now, we actually have tied both of our hands behind our back, and we're sticking with the point of view of Shannon's information theory and just asking, what signatures are there of organization and memory in a process that are revealed by how the block entropy curve converges to this asymptotic, this linear asymptote, right? So last time we talked about this excess entropy, which first point was it's different from the rate at which a process produces information. That's given by the entropy rate, this asymptotic slope. And it's a first cut at looking at what controls this rate of convergence to seeing the intrinsic randomness. Probably the most evocative interpretation of it, which we didn't derive, but the derivations are in this paper here, was that it's the mutual information between the past and the future, which brings us right back to Shannon's notion of a communication channel, but we think of every stochastic process and dynamical systems now as a communication channel, where in the present moment, there's some history stored in some architecture. That's the spring question, what's that architecture? And then that gets used to produce future behavior or to generate information in the future. So we have something like a channel utilization. The excess entropy is not really a channel capacity because that phrase was already defined in communication theory to be the largest information transmission rate across a channel, maximizing over all the inputs. And here we have a process that in some sense already generates its input, right? The present moment, the input process is the past it generates, so that's actually fixed, the input's fixed. We're not doing some kind of engineering maximization or optimization. So, but you call it information transmission rate, that's a little slightly confusing term, or just the channel utilization when we think about the system as a channel. Okay, so we're just going to keep pushing this. And in particular, I wanted to enrich the kinds of processes we've been looking at in terms of the excess entropy first. So finally, I'm going to give a definition. I mean, I almost used the phrase, or probably did accidentally use the phrase. So given a process, we're sort of interested in what the different classes are. So I'm going to talk about finitary processes that have finite excess entropy. We need some notion of finiteness in this. Finite memory, although I'm hedging my bets as I say that because, as we'll see, even in the first couple weeks of the spring quarter, the concept of memory actually needs to be elaborated a little bit. Just like we've taken the concept of information and gone from it's just degree of uncertainty and unpredictability and elaborated that to be, for example, this apparent mutual information between past and future, the excess entropy. So finite excess entropy, finitary process. The examples we looked at before, if we're looking at the length L approximation of the entropy rate, we noticed that converge from above. That was the entropy convergence picture. And that either happens at a finite L with a Markov chain, a finite order Markov chain, or in sort of the general case, I showed you a few examples, there is this eventual convergence, but it's an exponential convergence. And that's a little bit the signature of finite also, this kind of exponential convergence of the entropy rate approximates h mu of L to the true randomness entropy rate h mu. But also lots of processes where this excess entropy diverges. And that might seem a little bit strange. If we were looking at binary stochastic processes, you might naively think, oh, well, it's generating a bit. How could there ever be more than one bit of information stored in a process? Well, that just emphasizes the framework we're taking, which is we have an impoverished view of the internal structure. So when this E excess entropy diverges, it's sort of hinting that there's something more sophisticated going on that's hidden from us. Internal state structure. But at this point, we have just the process and the word distributions to work with. We don't have a notion of discovering what the intrinsic states are, but we have some signatures. So I want to go through a couple examples here. So if you remember from your homework, I sort of dragged you through the proof that the even process, although it's a two-state hidden Markov, or I should say, it can be described by a presentation that has a two-state unifilar hidden Markov chain. So you think, oh, it's very finite. Golden mean is also two-state. But it's not approximated by any finite order Markov chain. It's not exactly described by a finite order Markov chain. It is an infinite order Markov process, which is puzzling because it has just two internal states. The golden mean process, very similar to it, is a Markov chain over two states, order one Markov chain over two states. So what's going on here? All that's different, in fact, between the two presentations, unifilar presentations of the golden mean and even process is just a different labeling of the edges, in a sense, a different measuring instrument. But the even process has that strange property of ones, when they occur in blocks of even number bounded by zeros. And evenness is this a kind of, it's a property certainly that requires looking at perhaps arbitrarily long sequences. Okay, so we'll go back over this and look at our entropy convergence curves. And then I want to we'll sort of show that this still falls in the kind of finitary case, and then talk about two examples that illustrate two different kinds of complexity, structural complexity. One is called topological complexity. We already saw some block entropy curves last time. This Morse-Tui sequence. We'll talk a little bit about how that process is generated. And then another kind of apparent large structural complexity, which I call stochastic complexity, where most of the structure is in the probability amplitudes over the word distribution. The topological complexity is which sequences occur and don't occur. Some rich set of restrictions on that lead to it having long-range correlation. Here, the long-range correlation is due to probabilistic properties. Okay, so first the even process. So if you remember, a simple way to think about this is that after every pair of ones, I can flip a coin. After every pair of ones, so output symbol probability, after every pair of ones, I can do a fair coin flip. Right, and we also talked about this having this countable infinity of irreducible forbidden words. The first forbidden word for this occurs at length 3. 0, 1, and a 0 is disallowed, because ones, if they occur, have to be in blocks of even number. The second forbidden word is 0, 3 ones and a 0. That's at length 5, and so on. So we can just kind of enumerate that. 0, odd number of ones and a 0. Those are all forbidden words. Okay, and that was the kind of the key point of proving that no finite order Markov process exactly models the even process. But I guess I didn't show you, but anyway, so here's the block entropy curve going out to about 18. Here I've tried to do the graphical interpretation of the linear asymptote and pulled it back. There's not a whole lot of excess entropy here. Remember, that's the y offset. Here we see, actually I'm showing you two different approximations. We've been looking at this h mu of L in the last lecture, which is just this conditional entropy. Condition on L steps in the past, what's my uncertainty in the next measurement here. You can also go back to the very original definition that was used, which is the block entropy over L. So in this even process case, I'm looking at the entropy convergence, both of these, h mu prime, the block entropy over and h mu, the conditional. And you notice that, so the one is just kind of a technical point, which is this conditional entropy, which is the solid line, converges much more quickly than the block entropy over L. In fact, generally, we don't use this. If you were actually to do approximations here and want to calculate things like the excess entropy is the area between the curve and this, you do not use this form. That as a statistic, in the limit of infinite L, it does go to h mu, but it goes very, very slowly. So notice how the conditional entropy form of this, which is just the difference between block entropy at length L and block entropy at length L minus 1, it comes right down, it gets right down to h mu here very quickly. And here, this block entropy approximate is just going very, very slowly. So you do have to be, it's kind of methodological point. You have to be careful about how you estimate these quantities. And there's some versions like this, the conditional, that converge much more quickly. Okay, so then if you remember our hierarchy, the entropy hierarchy, where we're taking derivatives, block entropy first, dl derivative takes us to the entropy convergence view, and we do it again, essentially the curvature of this. And so this is the predictability gain. When this is large in magnitude, it means the symbol length we're at is very informative. So initially, pretty informative. The second measurement's not very informative, but the third one is. Right? There's a large change. There's a large reduction in my apparent entropy rate and the apparent randomness of the source. So that means there's a big predictability gain. What's going on at length 3? Oh, 0, 1, 0 is not allowed. That's an important restriction, which, like as we talked about before, when we looked at the mosaic of word distributions, it cleaves out a whole set of forbidden sequences. Very informative. At length 4, the next measurement not quite as informative. At length 5, very informative. Why? 0, 3 ones and a 0. So of course, we have the machine to look at, so I could go through and write down this irreducible forbidden word list. But if you just wanted to, if I gave you a process and just the word distribution, you didn't have a model for it, you could just calculate these curves, assuming you have enough data, and see that how these curves are converging. It's telling you a little bit, kind of hints at that there's some structure in the process. The shape of the curves and their oscillation doesn't immediately tell you what that structure is, but it gives you some hint, and therefore, this is your first cut in empirical analysis. You'd say, oh, I should do some more modeling. Okay, so we have about a bit of past-future mutual information. We do notice seems like in the entropy convergence, pretty well behaved. We talked before about how that's sort of typically for finitary processes an exponential decay, and so here's just a fit to that to show you. So this is the difference between the entropy rate approximate and the entropy rate, so just the distance above the curve, and then fit on a semi-log plot showing that this basically decays 2 to the 1/2 times L. It's a nice fit. Okay, so that's sort of a typical example. So although it's infinite order Markov, between you and me, because this prox is exponentially fast, you just go out to some length and you're pretty close to getting the entropy rate, a decent estimate. You'd have to be interested in very detailed questions to want to go to large L for a process like this. Just cut it off and call it a day. Okay. So, or the other way to think about it is that the evenness property is not, which has this potentially infinite range organization in it, blocks of even number. It doesn't control the statistical core of the process. It's there, but the subset of sequences which contribute to what you observe and have that property doesn't have a lot of probability attached to it. This is really effectively looking like a finite memory process. Okay, so it's kind of a faux infinity here. It's a finitary process, one bit of excess entropy. Okay, so let's go back to this Morse-Tui sequence. I mentioned before, when we just did a quick pass by it in talking about excess entropy case, that this is the same process that the logistic map or any period doubling system emits at the onset of chaos when you look through it with a generating partition. It was actually, the process itself was invented in the 20s and 30s by two mathematicians, Morse and Tuohy. Later on, we were able to show it's actually a context-free language, for those familiar with the Chomsky hierarchy. And the way it's generated is with just two simple production rules. So these are called string production rules. And there are two rules. If I have a zero, if I have a string, I come in and I apply sigma symbol-wise, and wherever I see a 0 in a string, I replace it with 0, 1. And wherever I see a 1, I replace it with 1, 0. So here's one example. I'm going to start with the initial string 1, but then do this 5 times. Okay, so the first thing is 1. Okay, and then I have a 1. That's just sigma. And I replace that with 1, 0. Okay? Now I do it again, which means I replace the 1 with the 1, 0, and the 0 with the 0, 1, so that now I have a length forward, which is 1, 0, 0, 1. Continue, right? This gets repeated. Again, like the first length forward will be the same, but now I'm replacing each one of these with longer set of length 2 words and so on. So this grows, the length grows, it doubles each time, because every symbol gets replaced with 2 symbols, and you get this. Obviously, this is a very deterministic process. There's no stochasticity in here. At first blush, you'd say, well, it's just 2 rules. That can't be very complex. But in fact, it is. So there are various properties it has. First of all, it's aperiodic. The sequence never has words in it that repeat exactly. There is a kind of infinite memory here, but it's completely predictable. So how are we going to... One way to see those is to do this block entropy curve analysis of it. Okay, first let's just look at the block entropy curves, which we saw before. This is our discussion at the end of last lecture. The block entropy grows, say, quickly at first, but then rolls over. Okay, and you might say, well, gosh, maybe that's the linear asymptote there, but it keeps rolling over more and more slowly. Let me also point out here, in these curves, the horizontal axis is actually in, the top 2 are in thousands, lengths of thousands of so. So this is the block entropy at over length 1,000 sequences, length 2,000 sequences, and this is the entropy convergence, h mu of L, well, in fact, both h mu prime and h mu as a function of 1, 2, 3, 4, 5,000 length words. The inset here is just blowing up around from 0 up to 30 length words. You can see that there are long ranges of L over which the predictability stays the same. As a consequence, down in the predictability gain, there are long regions of non-informative word lengths. I keep measuring longer, increasing my window, and it doesn't tell me, it doesn't give me any more predictability. And then there are just these sort of isolated word lengths where suddenly it's a little bit predictive. So that's one way you can think about these in the predictability gain plot. Mostly it's 0. So you're going to longer words. The average information gain is 0, except at particular places. In fact, the word lengths where you get some predictability, the interval between them gets longer and longer. Gets sparser and sparser. But they're still there, and that kind of hints that there is sort of long-range correlation in this, that it could have some kind of infinite memory. It's a little hard to tell from the block entropy curve or the entropy convergence curve what E is doing, but in this case it turns out that you can actually solve in closed form for the entropy rate approximates h mu of L. So here's the result of that. Not very sort of suggestive when you first start out, but let's look at the general form here. Basically it goes like 4 over L or 2 over L. So these different sort of windows, when L is between, in a certain range, between 2 to the k plus 1 and 3 times 2 to the k plus 1, then you have this, and then there's another sort of next phase where it goes with a different coefficient in front. But basically, it's going as 1 over L, which of course should mean that if you're summing or integrating things up like we do with the entropy convergence, you might have an infinite area, which is what the excess entropy is. Okay, so we have this 1 over L convergence of the entropy rate approximants. Well, first observation is that at infinite L, the entropy rate's 0. This is a completely predictable process. It just takes a really long time to get there. It takes an infinite long time to get there. So perfectly predictable, infinite memory, and aperiodic. So this was the initial mathematical interest in this really simple set of production rules, sort of the harbinger in the 20s and 30s for formal language theory and computer science. And then you can also sort of take this convergence and explain the block entropy curve. It grows logarithmically. So the idea that you're reaching some linear asymptote E plus H mu L, it just keeps rolling over ever more slowly, ever more slowly. And so, yeah, Chris, yeah. Yeah. Yeah, okay, so the question is, you're asking about these distances here? Yeah, that's actually given in the solution here. You can see there are these two different blocks. There's kind of 4 over L and 2 over L, roughly, for this. And so that's given by these different bounds on where those regions apply. And they get longer and longer. They double sort of each time. Yeah. And you can see their importance, their net contribution to improving your predictability is not much. But they're still there. They get smaller and smaller, 1 over L. So it's a process, very easy to generate. But now you might say, where in this process is there infinite memory? Well, there is an infinite memory, right? Because the way I'm generating this, I need to remember the previous string. So I have to store it somewhere. I can't just produce the next symbol without remembering my length 32 or length 64 word, right? So there is an infinite string register here, if you will. There's some device is storing this. When I go from 2 to 4 to 8 to 16, I have to remember the previous word. So there's a hint that you need that amount of memory. That's not really a kind of a computational device, but it is talking about the storage that's required to implement the algorithm. So just saying, oh, it's these two simple production rules it's these two simple production rules operating on an infinitely extendable register that can store a string of any length. Okay. So we can also look at approximations, given the analytical form we have, of the excess entropy, see how it diverges, try to convince ourselves this is an infinitary process. And so here I've got sort of like the previous plots with the entropy convergence, 2 different statistics I could use to pull out the excess entropy at length L. So one is just this term that we're summing up to make the excess entropy. So just the difference between the block entropy and this memoryless source minus H mu L. Or I can look at a block of length L and then look at a past of L over 2 and a future of L over 2 and then calculate that joint distribution. And then from that calculate the mutual information between them. So that's what the prime is, E prime is. And they have slightly different convergence properties, but they seem to be pretty well behaved. And lo and behold, it also has, you can show yourself that either of these has this kind of logarithmic growth. And therefore, the excess entropy diverges. And this is sort of a general property for people who studied some statistical physics of phase transitions. There's a class of processes called critical phenomena that have arbitrarily long-range spatial and temporal correlations. And this is one example of that kind of process. Right? Physicists would say, oh, the material, it's at the critical, or the liquid, or whatever is at, a critical point, and we have these long-range temporal and spatial fluctuations in structure. And here, we're giving you a way to measure this. In fact, in other work we've done, we use or have sort of proposed the excess entropy is this very generic way of measuring the structure in any statistical mechanical system. So there's this wonderful phrase, when you're analyzing a statistical mechanical system, like a spin system or say a set of atoms or something like that, you try to find the order parameter. Well, most students that are paying attention in statistical mechanics go, how do I know what the order parameter is in this new system we're analyzing? And it's, well, here, we do it this way. And it's never, you're never given a procedure for how to find an order parameter. So hint to people in statistical physics, try the excess entropy. It works remarkably well in all the cases we've studied. You don't have to worry about in your spin glasses with an overlap function or two-point correlation function and so on. This excess entropy is a nice place to start if you want to pick up some hints of the structure in a system where you don't know what the kind of right order parameter is initially. That doesn't mean it's easy to calculate, and so many order parameters that are used, magnetization in spin systems, they're very simple statistics that are good enough to capture most of what's going on, but E is a nice one.
Is E, typically your order parameter is 0, 1. Is E.
Well, magnetization is this fraction, right? What's the fraction of upspin, say? Mm-hmm. That would be the information analog of that would be looking at H of 1, right? The block entropy where the blocks are length 1. Which at least in this picture, you'd kind of guess, well, that's kind of crude. We should be able to do better than that. But that's fine for your two-dimensional easing spin system that kind of gives you a picture of where the phase transition is and critical exponents and all that sort of thing. So we might have some time to talk more directly about spin systems. I know I've been kind of alluding to them. They're, in our language, our current language, they're Markov processes of some order R, where R is the range of interaction in the spin system. Okay, so this is complex because of these kind of restrictions over longer and longer words. These complicated restrictions get built up by the production rules. Not really so much the word probabilities. So to show you a complementary example of where infinite complexity of a kind shows up, due to the probability structure over the word distribution, we can look back at this simple non-unifilar source. So now you're starting to see why I keep bringing these examples back and try to at least ground them. Remember this guy you can pull out of the logistic map. Okay. But also we talked before about this, right? So this is non-unifilar because if I'm in state A and I see a 1, I don't know uniquely what state I'm going to. All right, go back to A or to B. If I was in B, that's a unifilar transition. If I say 0, you know, you're going to A. Saw 1, I go to B. But from that point forward, I see 1s. I have to see a 1. It's like golden mean. I get confused. I know after a 0, I definitely am in state A. With probability 1. I've synchronized, which we'll talk about a bit. From that point forward, after the next 1, I can be in A or B with equal probability, and so on. If I see another 1, well, the chance that I'm in A goes down a little bit. Chance I'm in B goes up a little bit. See another 1, more and more. So as I see more 1s, my guess as to what the internal state probabilities are is changing slightly, and that changes how well we can predict. So we have to keep track of that. So that's sort of the main reason this thing is an example of a kind of infinite memory. But let's go back to where we were just talking about processes and models weeks ago. What's the entropy rate? Well, we have that formula, but that only the closed form formula for the entropy rate, the state average branching uncertainty. But that only applied. We had a version for Markov chains, and we had a version for unifilar hidden Markov chains. We talked a bit about why non-unifilarity means you can't use that formula, right? We're interested in the entropy rate of the generated process. When we have a presentation that is unifilar, we can use essentially the entropy rate of the internal Markov chain state sequence as a proxy for that. But if it's non-unifilar, we break this mapping between observed sequences and state sequences. Therefore, the quantitative properties don't carry over, so we can't use it. But we talked about that at some length. So this is a puzzle. How random is the simple non-unifilar source? I can't calculate the main statistic here, the entropy rate. At least not yet. So more product placement spring quarter. We'll do this. We'll give you closed form for it too. Okay, but at this point, we're just doing information theory over the word distribution. So we have our block entropy curves. The question is, what does it tell us? What? So here is the block entropy as a function of L for the SNS. If you can kind of see this, well, it's not very featureful. Actually, at length 1, it looks like it meets its asymptote. Well, not quite if you look at it closely, but gets up there pretty quickly. And if I do the linear asymptote and bring it back, there's not a lot of excess entropy here. It's like well under a bit. It's about 1/5 of a bit. But it does look like it converges quickly. So what's going on here? It's a little clear to see the convergence properties in the h mu of L plots. I have the two approximates here, but just look at the solid line. It's actually around, where is it? Length 2, that this comes down pretty close to the asymptotic entropy rate. Okay, so again, between friends, you can probably do well at characterizing the SNS process with just the statistics over length 2 words. You'll capture, I don't know how you want to say it, 90% or 95% of what the process is doing. The predictability gain, well, it starts sort of informative, gets a little less informative, then kind of just poops out. So it's not telling us a whole lot about what's going on here. But you go, wow, that looks like a really finite memory process. Therefore, it should look like the things we talked about before, where we have this exponential decay. It gets there fast, but maybe there's still some tail down here that's getting close exponentially, and so you can just go fit the entropy convergence h mu of L minus h mu to an exponential. Well, actually, it's converging more slowly than an exponential. You say, okay, it's a power law. You can try to fit this form here in a semi-log plot, and it's decaying faster than a power law. So it's not finite memory in the sense we talked about before when we had exponential decay in this kind of generic finite memory case. So something's going on here. So this sort of block entropy analysis, again, gets our foot in the door. It's just suggestive, but we can't say a whole lot more about this, at least for a few weeks. So, yeah. Okay, so that's just some examples of what can happen. It's been good to start with some relatively simple processes, finite memory, Markov chains, that kind of thing. But the really interesting processes we tend to study now are these infinite ones. But information theory begins to fail us in this. So we need a new set of tools. There's a little more we can do. So what I talk now about is this another one of these information measures we can pull out of the block entropy curve. It's related to a property called synchronization. And then next week, we'll talk about some other measures and also try to enrich the tools we have from information theory. So we're going to kind of push information theory pretty hard through next week. And then I will, probably the last half of the lecture, certainly the first lecture of next quarter, kind of throw up my hands and complain about information theory. But for now, we'll keep working with it. Okay, so what is synchronization? Okay, so imagine that you were in your lab doing your great job at taking data and analyzing. You had a model, but then you left for the evening and came back and the experiment was still running and you sort of forgotten what was going on in the process in terms of what state the thing is in. But you still have a good model of it. So when you come back in the lab the next day, you don't know what the current state is. So the question is, how many measurements do I need to make so that I can see what the internal state is? That's also related to how much information do I need to extract so that I can predict at the rate that's determined by the entropy rate itself. So here we're assuming we have a model that tells us what the hidden states are and what the observation process. So we'll have a hidden Markov model of this, but I'm not going to tell you what the starting state is. And then you start making measurements, 1, 0, 1, 1. And the question is, how does your best guess as to the internal state distribution, how does that change? And then we say we're synchronized when I know exactly what the internal state is from these observed sequences. Okay, so now there's a way to express that idea in terms of the block entropy curve. So here we have the generic H of L curve, and quantitatively, we say that we've synchronized a process when we're at an L so that H of L is very close to the linear asymptote. That, for example, the 2-point slope here would be close to the entropy rate, so on. Okay. So we're synchronized when beyond some word length L prime, basically the block entropy scales with that linear asymptote, E plus H mu L. Right, L prime being the length at which you get a good approximation, or actually C, like in the case of the golden mean, you can actually estimate H mu. Or that's the length at which you can do optimal prediction. So the trick here is going to be exactly the same we did before. Remember, before we were talking about the entropy hierarchy, first we took these derivatives. Well, I've been showing you derivatives of the block entropy, all those curves for the examples. And then we started integrating. First we integrated the del squared to get the predictability gain, which was a kind of redundancy. Then we integrated that and got the excess entropy and spent a certain amount of time talking about that with this interesting interpretation. It's the past-future mutual information, and I'm going to do it again. Okay, so what did we do before? We had some asymptote and then some function that was converging to it, and we calculated an area, an integral. It's the same thing here. So I'm looking at the block entropy curve. I have this linear asymptote, and I just want to calculate the area there. Why? Well, it's pretty simple. The larger this area, called the transient information, it's kind of a proxy for this taking a long time to get down there. If t was small, that would mean I came up to linear asymptote quickly. It's just that simple an idea graphically. So here's we're just summing up these contributions. The difference between E plus H mu L, this is positive, right? Because the block entropy converges from below. We just sum up those differences. So the units here are actually bits. There's like an implied, integral dx in here. There's like a symbol here. So the bits of the transient information t are bit symbols. So to make this a little more timely and also intuitive, the break is coming up. So we imagine we're going to go on vacation here, going to Tahiti. And we know something about it. We have a good model of it, right? This is the middle of the South Pacific. The trade winds, things don't really change that much there. Prevailing winds always come from, the northeast. And we know that on Tahiti, there's a 5-day weather cycle. We have 2 days of rain, followed by 3 days of sun. Okay, so we know that. A couple of the immediate information consequences that we know it's a period 5 cycle. Therefore, H mu 0. It's completely predictable. And it stores a certain amount of, it's the weather system down there, stores a certain amount of information. The past future mutual information, excess entropy, is log of the period, or log base 2 of 5 bits. Okay. But it turns out we have more pressing questions than these information numbers. We want to know, how am I going to pack? What should I pack? What to wear on the plane? Should I hop on the plane with my umbrella next to me, so when I hop out, go down the gangway, I'm shielded from the rain? Or should I have my shorts and dash out the plane, ready to hit the beach? So how do you dress? Okay, so here's the basic picture of this synchronization idea. So we know that, so this is the picture of the actual weather system on Tahiti. It's got 5 states, and it goes rain, rain, sun, sun, sun. Rain, rain, sun, sun, sun forever. However, I've been busy. I haven't listened to the news or read any weather reports. So if I haven't made any measurements, what's my best guess? Could be at any phase of that period 5 cycle with equal probability. So here's my picture, our picture of what's happening in Tahiti. This is what actually is happening, but we don't get to know that. And the weather reports aren't so informative. They're telling us, dear New York Times weather section reader, this is the phase of the Tahitian weather cycle. All it's going to do is tell us whether it's the previous day was rain or sun. Okay, so I read the paper and go, oh, rain. Oh, damn it. I want to go have this nice, warm, lay on the beach vacation, but it's raining. Okay, so now, of course, this is moved forward. It started in B here move to phase C. We don't know that, right? All we know is that this guess we had, uniform distribution over the 5 phases, has been updated by the information that it rained. So what phase could we be in such that it rained the previous day? Well, we have the model, so we can look at all those days or phases where the previous day was rain. And so our guess as to the internal state distribution goes from uniform down to these 2 phases, which I guess is B and C, being 50-50. Right, you see that? There are only 2 days consistent with the previous day raining. So that's good, right? So as an observer, my guess as to what the internal state is has now sharpened up a bit. It's still 50-50, right? The next day still could be rain. When I hop on the plane, it still could rain or be sunny. So, and then finally, we read the paper the next day, the day we're hopping on the plane, and we see it's sun, right? So then our uncertainty, uniform uncertainty between phases B and C is now, we know that exactly with certainty what phase the weather cycle is in. That would be D, because it's consistent with, it's the only phase or day that's consistent with rain, sun. Right, so the picture here of synchronization is I'm incrementally making these measurements, and my sort of posterior guess is updated by that and narrowing down until finally we're, quote, synchronized, and we know exactly what state we're in. Okay, so, right, so umbrella goes in the checked baggage, and you wear shorts on the plane because you're hitting the beach as soon as you land in Tahiti, right? And you can go through and calculate this transient information, about 4 bits, this whole process of measuring the 0 and 0, 1. The information we're talking about here is how our uncertainty in the state distribution has changed, improved and improved until there was no uncertainty in the state. And you integrate that up, and that gives you this T of about 4 bits. Right? This isn't information in the 0, 1 sequence, rain or sun. It's in how our model in our head and the induced probability distribution was changing. Right? So, which is an important aspect of information that often goes unspoken. Many of the kinds of information we're talking about have to do about our expectations, not about some property of a process. Now we have measures of that, like entropy rate, but this one has to do with the model we're using. And you can even go through this exercise. Imagine you had an incorrect model. You could still do the same type of exercise. Wrong number of states, a different notion of, it's period 4 or something like that, yeah.
I just wonder, how does this T relate to the number of symbols you need to see? It seems to me if I see 3,
right.
If I see 3 symbols,
right.
I know which word it is.
Right.
So I'm just trying to see why do I need 4 bits?
Right. Well, we'll get to that.
Okay.
Yeah. Right. So there's so first of all, this will be averaged over all possible experiments you do. And an ensemble of Tahitian vacations. Okay.
Isn't it free the maximum I need to see?
Right. So this is not information. It's about how your internal model has improved. You have a certain amount of uncertainty. Right? Up here it was log base 2 of 5 bits.
Yes.
And then it reduced down to 1 bit and then down to 0 bits. And I'm integrating that up. Right? So it's about you.
It's about me.
Right.
It's not about what I need
right.
to see.
But it's a fair question. But it's a slightly different statistic.
Yes.
Give me the average number of measurements I need to be synchronized. Right.
It's a different measure.
Yeah, right. Right. Complementary. Right. Well, in fact, I guess that's kind of this, right? We sort of have this notion that I started out with, which is your question, the idea that this H of L would come up and actually hit right here, and then that L prime, that would be the answer to your question. That's different than the area here.
Yes.
Right. In fact, I can sort of draw different monotonic curves here that'll have different T's and still hit at the same L prime. So, and we'll see that actually T is giving us some maybe unanticipated additional hint of how a process is structured. Just to give you maybe a statistic that's a little more directed towards interpreting T. T is a slightly funny statistic, and next couple slides will kind of show why. Okay, so to be a little more formal about this, the observer's got some state-based model, transition structure, and then our criteria for synchronization is that the estimate at some length of the transient information is 0. That we're summing up these components. So that's where the curve, block entropy, meets the linear asymptote. And the goal here is we're looking at how the observer's guess as to the internal state distribution gets updated, and the criteria in terms of the state distribution is that we just have a delta function on one of the states. Okay. So we can define a related measure of state uncertainty. It's more directly related to measuring the uncertainty in our state distribution after we've seen some sequence. So what we're doing here is we're just looking at, this is a conditional entropy, this inner sum here. Given I'd seen some word of length L, what's the observer's uncertainty over the state? And then we average that over the process generating words of length 1, length 2, length 3. And then sum that up. So that's we call it just the state uncertainty at length L. And then the synchronization information, we just add that up. This is maybe more directly related to how I explained going from the 5 phases of TED to being uncertain over 2 states and so on. So we just add this up. That's more directly the information that we've extracted. However, T is really easy to pull off from the block entropy curve, right? So the question is, what's the relationship between this integrated state uncertainty and this number that we've pulled off, which is just the area between the linear asymptote and the block entropy curve? So although there's a more general theory that sort of simple cases are, and this is what's covered in the paper, the regularities unseen paper, you can show that there's a direct relationship between this transient information, which is easy to calculate from the block entropy, and the synchronization information in the case that you have an R-block process. So there's some other contributions here that depend on the entropy rate and the range, the order of the process. However, for periodic processes, like the Tahitian example, these are essentially the same. I mean, these are the same, right? Periodic processes, H mu is equal to 0. So at least in the Tahitian case, these two things are the same. T is the integrated improvement in state uncertainty. When we have a slightly stochastic process, there are these other terms out here, which we need some more technology to understand. Right, so again, so this is, T is easy to interpret at that area. In case of periodic processes, well, H of L would then go flat at some point, right? Come up to E log of the period, then that area would be T or S. And it's the information you need to extract to be synchronized. Let's do a couple of examples here. Easy one, always the sort of dead horse to be flogged, the fair and biased coins. Again, you can just read this off of the curve, the block entropy curve. Nothing to do here. Not only is the y-intercept of the linear asymptote 0, excess entropy 0, but so is T. IID processes are sort of at their linear asymptote from the get-go. More interestingly, is to go back to the period 5 process. So the Tahitian example is just one particular period 5 process, right? 2 days of rain, 3 days of sun, repeated. Well, there are really 3 distinct length 5 templates that are equivalent under permutation and under 0-1 exchange. So they're informationally the same. So we just have these 3 different templates here. So, I mean, this is the Tahitian example, except now we had 2 days of rain, I coded those as 0s, and 3 days of sun, I coded those as 1s, an example. But that's the equivalent template, okay? But then we have these other distinct templates. First point is, again, it's periodic. These are periodic processes. They're all predictable, and they all have the same past-future mutual information, the same phase information in this case. So H, mu, and E are useless for distinguishing between them. However, this synchronization, you can kind of imagine, it goes, could depend, right? Here, so if you look at this template word, if that was the weather cycle in Tahiti and I saw it was sunny, I immediately know what the phase is. However, that's sort of compensated by the fact that most of the time I'm going to see zeros, and I won't know when I see a particular zero where in this block of 4 it is. Therefore, on average, that adds a lot more uncertainty. And it turns out that this kind of template for any period P word, 1 and a bunch of zeros, is the hardest to synchronize to, even though there's one big upside. If you happen to get lucky, there's one phase of it that you can get quickly. So here, let's just do this analysis again, block entropy, entropy convergence, and the information gain for those 3 different period 5 processes. Again, entropy, rate, E don't help us here. They're all the same, right? Entropy rate 0, and E is all the same, log base 2 of 5. But what we can see here is that we get to the asymptote here, which is length 4, in different ways. So the isolated 1 and 4 zeros, that takes the longest to get there. The fastest one was this one here, 1, 1, and 2 zeros. That was the Tahitian weather cycle case. You can get there fastest. In the entropy convergence plot, they get down to 0 entropy rate in different ways, actually in different lengths. But of course, they have the same excess entropy. So it means for each case, the integrated area has to be the same. That's the definition of excess entropy. And you can kind of see that if you look at the solid line, that's the one that took longest. But the area under here is E for that, but it's got to be log 2 of 5. The one that took longest to get, the quickest to get up there was the Tahitian cycle. That kind of exceeds this, but then it dips down below. Anyway, the areas are the same. But at least there's some kind of signature that we can see in this case that distinguishes these template words. And then, of course, in the predictability gain, you can see that different word lengths are more or less informative depending upon which template cycle you have, which prototype cycle you have. And then, no surprise, if you calculate t, you have different t values. So that's nice, right? The largest is for the isolated 1 case. The lowest t-value, quickest synchronizing is that Tahitian cycle. So that's good. At least for periodic processes, H, mu, and E are not helpful at all. But T lets us distinguish them because it's tracking how we synchronize. That sort of brings up this interesting question. There's a view of the world that everything is periodic. That's called Fourier analysis, right? So you can ask, you can just look over all periodic processes, and there's a way to, just a little number theory to calculate what these unique templates are up to permutation equivalence and 0-1 exchange. And so what we have here is just looking at the period, so say period 15, and then calculating the transient information for all of the distinct, 15,000 whatever words of length 15, the distinct templates. So this is the distribution, that's the min, that's the maximum. So what's interesting here is now we start to realize that there's, even for periodic processes, which probably up until today we were kind of considering boring, there's a wide diversity in how they will appear to us and how we can synchronize to them. So these are the estimated upper and lower bounds, and it turns out there's an analytical theory for this. So the maximum transient information goes like this in terms of the period, half p log p. And with p log p, that's not related to any information that I can think of. It just worked out that way analytically. Just a coincidence. The minimum t, the lower bound here, goes like this, a half log squared of p plus log p, and captures it pretty well. So you can describe this, anticipate the diversity of synchronization for even periodic sequences in some detail. So we've got this fairly detailed roadmap now, and all of this was just looking at what nominally is at least a straightforward to calculate function, just a block entropy curve. So we have, block entropy, entropy rates, predictability gain, excess entropy, total predictability, excess entropy, and now the transient information. So we went up the hierarchy taking derivatives, and we came back down and interpreted all these constants of integration, or these summed quantities, areas. They all have an information theoretic, kind of a functional meaning to them. Synchronization, memory, information generation. Yeah? Please.
Okay, so you can get the maximums from the minimums T. Can you also get the distribution of T between the two? Like for all periodic processes. Because it looks sort of like that in this curve, like you have more periodic processes where the minimum and the maximum. I don't know if I'm reading that right.
Oh, right. Yeah, I'm surprised you can see that on this video over Skype. Right, there's a lot of density down here. Is that what you're talking about?
Yeah.
Right, so there are lots, yeah, so the preponderance, there's this huge range. Right, the upper bound here, for period 15 or period 20, whatever, we know what that sequence is. That's the, if we're looking at length 20 words, the sequence that generates the maximum T up here is the isolated 1 and 19 zeros. Then there's this distribution down here. Turns out we actually know what these minimum T sequences, they're called de Bruijn sequences, but let me not go into that. They're 0, 1 words, again, they're sort of equivalent under permutation flip, where each one of the words, the subwords, occurs once. That's actually, turns out, used in coding theory. Quick to synchronize. That would obviously be important when you're trying to synchronize two systems, control systems or computer systems. So this is used actually in satellite control a lot. Right, we have the GPS system, all those satellites up there talking to each other, and they need to stay, the very way GPS works requires extremely tight time synchronization between the satellites. First of all, they have to correct for special relativistic and general relativistic effects, very, very high order effects. And then the timing, when the signals come down to us, it's all the information about where you are encoded in the timing. So they use these easy to synchronize codes. They're constantly transmitting this stuff in the kind of background control channel between all the satellites to keep them synchronized. Right, so here's the tableau. Again, this will be the information sort of proxy for yet another classification scheme. Well, not quite a classification scheme, but at least there's one picture you can keep in mind. We have the kind of generic case, block entropy growth. There's this linear asymptote, the slope of which is the entropy rate. The y offset is the excess entropy, or the distance between your h of L and the memoryless source that goes through the origin. Then this area here is the transient information. So a very integrated picture. Each of these adds something to our knowledge about a process, and in principle, well, one can write code like is built into Campy, Sage. You can calculate all these things now. So the lab lets you calculate the block entropy curves, and then it turns out to accurately calculate even something like the excess entropy, which is this time symmetric quantity, past and future mutual information, or future past, doesn't matter, it's the same. It's actually quite hard, and we need to do a little more work in the spring quarter to be able to calculate this accurately. H mu, fine, but we can at least approximate H mu well, but E's harder. Okay, so what are the consequences of this? Now I want to really just, now that we have this sort of summary of all these different things, we spent 2 days building up this chart here. Well, actually more than that. 2 weeks, but here we are, this tableau. It also gives us a way to talk sort of graphically about problems you might encounter. So in particular, there are different sources of uncertainty, right? One was just how well can I predict. The other is how uncertain is my state estimate, right? So there's different kinds of uncertainty here. So we'd like to sort of untangle these distinct sources of randomness that we have, or be a little more hard-nosed about it. What are the consequences for quantitative estimates of the degree of randomness if I ignore something? If I'm not aware of something like the excess entropy, I'm not aware of something like T, and I go off and try to calculate the entropy rate, I'll be using statistics that don't take this general behavior into account, and there's some consequence for how it messes up the estimate of even how random a process is. So the general lesson here is, even if I focus on, how random is a process, I have to keep track of how structured the source is. And then we have now a couple of properties that indicate different kinds of structure, synchronization, and so on. So we can now use that tableau to try to answer a couple different questions. So what happens when the observer ignores the convergence of the entropy rate, or you ignore the fact that the process might have some positive excess entropy, or assumes or ignores synchronizations, or assumes you're synchronized. So each of these cases we have a way of talking about this and seeing what the consequences are from the information tableau. Okay, so the first lesson is disorder is the price of ignorance. Right, so we're going to ignore a process's memory, and the framework we've got set up is this first notion of what memory is that we have to work with is the excess entropy. So I'm going to look at the world in terms of, I just want to measure the entropy rate, and I don't care about how much memory the process has. So what's the consequence? So here graphically, we've got our generic H of L curve. We stop at some word length, and we try to make an estimate of the entropy rate. Well, if I try to fit the H of L curve using E equals 0, that's the same thing as an entropy estimator H prime. That's that block entropy over L. That's tantamount to my assuming that the source has no memory, that it's an IID process, which means I'm going to look at H of L, divide that by L, or the other way to think about it is that I'm kind of assuming there's this linear function that goes through here. Contrast that with being aware that there might be some excess entropy or memory in the source. So now my fits are straight lines where I fit to try to get the 2-point slope correct, like this. Notice that my estimate here of the slope is much lower than this IID approximation. So if I ignore the memory in the process E, I overestimate the entropy rate. The process looks more random than it is. In a sense, by ignoring memory, I've sort of converted the memory into apparent randomness. Right? So the memoryless approximation of an entropy rate is always larger than allowing that. It's like you're doing a curve fitting, except rather than forcing the curve that your straight line you're using to be pinned to 0, you let it float. Well, same thing as doing a 2-point slope approximation. So again, by ignoring E, H mu increases. You can also assume that you're instantly synced, that somehow you know what the memory is, E. And then now we've got some approximate here, H mu wide hat. So here I'm now fitting with linear curves that go through E, some point along the H of L curve, and you notice that the upper line here would be the true linear asymptote. And if then both of these curves are being fixed down here. If I then take an empirical estimate of the block entropy to fit that, the slope of this curve, the entropy rate, is lower than the true case. So if you assume you're synchronized or that the process has E bits, then that can lead to false predictability. I mean, what you really should be doing is sort of estimating consistently some approximation of the excess entropy at finite length. So you let the curve hit just like in the previous picture. So the process looks more predictable. You'll underestimate the entropy rate here. Yes. yeah. Have I got, yes, a piece of real estate for you. Okay, so you can also assume you're synced in a different way. Basically, you assume that the entropy convergence has already converged, that I'm seeing the entropy rate here. And that is, the graphical version of this is we have our block entropy curve. Here's the sort of true case, E plus H mu L. And now I'm fitting with a parallel line at some finite L. And that necessarily shifts down my excess entropy estimate. So if I assume I'm synced in this way, that I can do optimal prediction, then I'm going to underestimate the amount of memory in the source. Anyway, there are different ways to take this information tableau and kind of turn it on its head and see what some of the consequences are, and there are trade-offs. I mean, when I introduce these information measures, they're kind of on their own term, but of course in any, kind of in the ideal situations, how they get defined, but in any real system, your intelligent agent walking through the world, you don't have infinite data, you have a bad model and so on. So when that happens with finite data and so on, in practical situations, these information measures cross-couple. And so ignoring them or misestimating them can have consequences for the other things you'd be estimating. So this all has to be done, really has to be done all at once. I mean, historically, probably, the first 50 years of the theory of dynamical systems focused just on one thing, entropy rate. That's all anybody was ever interested in. There are 10,000 papers on estimating the entropy rate, never even thinking about that they needed a concept of memory and had to use that to help improve their estimates of randomness. So you can kind of look at that whole literature with a little bit of kind of a skeptical eye when you realize how these things are coupled together. Okay, so there it is, the entropy hierarchy, right? Just sort of increasing in level. We took these derivatives, going from block entropy to slopes to curvatures. Again, the 2 lectures were just going up to this level and then we stopped. That doesn't mean it can't or shouldn't or doesn't go on. Really, there can be other processes where the 3rd derivative could be interesting. I don't quite have the intuitions or the vocabulary to describe what that would mean, but I guess in a practical situation, if it became important, I would definitely look at it. And then we started integrating these curves, looking at the constant integration, total predictability, showed that it was related to the redundancy, the excess entropy, past future mutual information, and now this transient information, which is tracking synchronization. So yeah, so when you study a process, you'd like to know all of these things. Transient information, excess entropy, total predictability, which is basically a function of the entropy rate. And so this is all in the context of just looking at the block entropy. So what we're going to talk about next week is using a slightly different type of joint distribution, kind of looking at past and the future and how that affects the current measurement. Here we're just looking at blocks and the statistics over blocks, over words. Next week, we're going to talk about what we know about the present moment in the context of the past and the future. Well, we already know one information measure for that. What do I know about the present moment given the past? That's the entropy rate. But we can also ask how much information in the present moment is shared with the future. So that'll give us sort of a richer picture and more or less exhaust how we're going to use information theory. Okay, that's it for today. I do have a bit of business, which is